Welcome back to the energy conversion lectures. In the previous lectures, we provided some introduction about the armature distributed windings. Also, we showed that the distributed windings have advantage and disadvantage. The main advantage of the armature distributed windings is improving the utilization of the armature. Basically, improving the utilization of the armature means we can use or add more coils in the armature and therefore increases the capability of the machine in inducing high armature back EMF voltage ER. The disadvantage of the distributed windings is introducing the slots harmonics. In this lecture, we will show that the distributed windings have another advantage and have another disadvantage. Basically, we will show that using the armature distributed windings will cause some amount of reduction in the induced back EMF voltage ER comparing with the concentrated armature windings. Based on this reduction in the back EMF induced voltage, the distributed windings will have advantage and disadvantage. The advantage is reduction in the magnitude of the harmonic components of the induced back EMF voltage ER, and the disadvantage is reduction in the magnitude of the fundamental component of the induced back EMF voltage ER. Let's get into the details. These two figures show two synchronous machines. The first machine represents two poles single-phase machine with concentrated stator winding consists of 3 coils. The other machine represents two poles single-phase machine with distributed armature winding consists of 3 coils. Basically, we need to identify and compare the impact of the winding types on the back EMF induced voltage of both machines. In previous lectures, we mentioned that the armature back EMF induced voltage ER consists of fundamental component and harmonic components. However, to simplify the analysis and the discussion, let's assume that the armature induced back EMF voltage ER of any coil has only the fundamental component and ignore the harmonics for now. Now let's first start the discussion with the concentrated armature winding machine. This figure shows the linear representation of the machine. As we can see, phase A of this single-phase synchronous machine consists of 3 concentrated coils. Note that these 3 coils are full-pitched coils. Now, as mentioned before, if the rotor sweeps across these 3 stator coils, each coil will induce a voltage at the terminal of the coil as shown. The waveforms of these voltages ER1, ER2, and ER3 can be drawn as shown. As we can see, these 3 induced voltage waveforms ER1, ER2, and ER3 are in phase or are aligned with each other because the 3 coils sides of phase A of the concentrated winding are installed in one slot. This waveform ER shows the total instantaneous sum of the 3 induced back EMF voltages ER1, ER2, and ER3. This phasor diagram represents the phasors of the three induced voltages ER1, ER2, and ER3. The sum of the three phasors is represented by the phasor ER, which represents the RMS value or the sum of the three phasors ER1, ER2, and ER3. It is very clear that the phasors ER1, ER2, and ER3 are in phase. We mentioned in previous lectures that since these voltages ER1, ER2, and ER3 are in phase and the coils are connected in series, then the RMS value ER of the total back EMF induced voltage is equal to the algebraic sum of the RMS values of the three induced back EMF voltages. Basically, the conclusion was if the phase coils are concentrated coils, then the total RMS back EMF induced voltage ER will equal to the algebraic sum of the coil's RMS back EMF voltages and therefore equal to 3E, where ER1 equal ER2 equal ER3 and equal to E. Again, the phasor ER is equal to the algebraic sum of the RMS values of the back EMF voltages ER1, ER2, and ER3. Now let's try to determine the back EMF induced voltage of this distributed windings machine. This figure shows the linearized representation of this machine. As we can see, this machine has three distributed armature coils which are shifted from each other by the slot angle beta. Note that these three distributed coils are full-pitched coils. That means each of these coils have coil span of 180 degrees electrical. Now let's assume that the slot angle beta of these distributed coils is equal to 20 degree electrical. As we can see, these figures show that coil A2 is shifted from coil A1 by the slot angle beta, and coil A3 is shifted from coil A2 by the angle beta. Also, we can say that coil A3 is shifted from the coil A1 by the angle of 2 beta. It should be noted here that these coils of phase A are always connected in series. It is very important to know that each of these coils will induce back EMF voltage when the rotor or rotor magnetic field sweeps or rotates across these three armature coils of phase A. The measured instantaneous back EMF induced terminal voltages of the three coils of phase A are as shown, where the voltage ER1 represents the fundamental component of the instantaneous back EMF induced voltage of the coil A1 of phase A. The voltage ER2 represents the fundamental component of the instantaneous back EMF induced voltage of the coil A2 of phase A. And the voltage ER3 represents the fundamental component of the instantaneous back EMF induced voltage of the coil A3 of phase A. It should be noted here that the induced voltages ER1, ER2, and ER3 are represented by pure sinusoidal waveforms because we assumed that the rotor magnetic field distribution is a pure sinusoidal distribution. Now pay attention to this important point. The sinusoidal induced voltages are not aligned because the distributed armature coils A1, A1', A2, A2', and A3, A3' are shifted from each other. As we can see, the voltage ER2 is shifted or lag by beta from the voltage ER1, and the voltage ER3 is shifted or lag by beta from the voltage ER2. The RMS values of these instantaneous voltages are represented by ER1, ER2, and ER3. It should be noted here that the RMS values ER1, ER2, and ER3 are equals because we assume that the number of turns of the three coils A1, A1', A2, A2', and A3, A3' are equals. This waveform ER shows the fundamental component of the instantaneous sum of the three induced voltages ER1, ER2, and ER3. The instantaneous back EMF induced voltage ER of phase A is equal to the instantaneous sum of the three instantaneous back EMF voltages ER1, ER2, and ER3 because the three coils of phase A are always connected in series. The RMS value of the total induced back EMF voltage ER of the distributed coils will not equal to the algebraic sum of the RMS values of the three induced voltages ER1, ER2, and ER3 because the induced voltages waveforms ER1, ER2, ER3 are not aligned. In other words, they are shifted from each other by the electrical slot angle beta. Basically, distributing three coils in three slots that are shifted by slot angle beta will induce three voltages that are shifted by the angle beta. Let's explain this statement in more details using this phasor diagram. As we can see, this figure shows the phasor diagram of the three induced voltages ER1, ER2, and ER3. It is very clear that the induced voltages ER1, ER2, and ER3 of the distributed coils are shifted from each other by the angle beta, where ER2 lags ER1 by beta and ER3 lags ER2 by beta. The sum of these three induced voltages can be represented by the phasor ER. Basically, the phasor ER represents the phasors sum of the three phasors ER1, ER2, and ER3. Now, if we assume that the slot's angle is equal to 20 degrees electrical, the RMS value ER of the induced voltage of the distributed coils in our example can be calculated as shown. It is very clear that ER will equal to 2.879 E, where ER1 equal ER2 equal ER3 and equal to E. This slide shows summary of the comparison between the 3 distributed coils machine and the 3 concentrated coils machine. It is very clear that the RMS value of the induced back EMF voltage of the 3 distributed coils in our example is equal to the phasors sum of ER1, ER2, and ER3 and equal to 2.879 E, which is smaller than the RMS value of the back EMF induced voltage ER of the 3 concentrated coils, which is equal to the algebraic sum of ER1, ER2, and ER3 and equal to 3E, where ER1 equal ER2 equal ER3 and equal to E. We can understand from this discussion and comparison that the 3 distributed coils in the 3 slots that are shifted by slots angle beta will induce 3 voltages that are shifted by the angle beta. Also, the phasors sum of these 3 phasors of the distributed coils is less than the algebraic sum of the phasors of the concentrated coils. This MATLAB Simulink model shows how to simulate the difference between the distributed and concentrated back EMF induced voltages. We highly encourage to perform this simulation model to understand the difference. Basically, this example simulates the 3 coils induced voltages of the concentrated and distributed coils. Now, if we divide the back EMF induced voltage in distributed windings over the back EMF induced voltage in the concentrated windings, we can introduce a new factor denoted by Kd and called distribution factor. Based on this new relationship, the distribution factor Kd in our 3 coils example will be equal to phasors sum of ER1, ER2, and ER3 over the algebraic sum of ER1, ER2, and ER3. Therefore, Kd will equal to 2.879 E over 3E and equal to 0.96, where ER1 equal ER2 equal ER3 and equal to E. The distribution factor of 0.96 means that the phase-induced voltage in 3 distributed coils will be only 96% of the phase-induced voltage of the 3 concentrated coils. In other words, the phase voltage of the distributed windings or coils will be reduced by 4% comparing with the phase voltage of the concentrated windings. It is worth to mention here that the factor Kd of the distributed armature windings is always less than 1. Now let's try to derive a formula for the distribution factor Kd using this general definition of Kd and this phasor diagram of the 3 distributed coils. Let's mark the phasor diagram of the 3 distributed coils as shown. Now if we draw a curve pass through the terminals of the 3 phasors AB, BC, and CD, the curve will form a circle. The center of the circle can be denoted by the capital letter O. The phasor AB subtends the angle beta at the center. The phasor BC subtends the angle beta at the center. The phasor CD subtends the angle beta at the center. Now let's focus on the triangle ADO. As we can see, the phasors sum AD of the three phasors subtends the angle 3 beta, or in general M beta, where M represents the slots per pole per phase. Basically, the number of slots per pole per phase M will allow in generating M voltage phasors, which in this example equals to 3 because we have 3 voltage phasors AB, BC, and CD. That means M will also represent the number of voltage phasors AB, BC, and CD, which are equal to 3 phasors. Now let's represent the numerator and denominator of KD based on the phasors AB, BC, CD, and AD. The numerator of KD, which represents the EMF induced in the distributed windings, can be represented by the sum of the 3 voltage phasors AB, BC, and CD, and equal to the phasor AD. However, the denominator of KD, which represents the EMF induced in the concentrated windings, and can be represented by the algebraic sum of the 3 phasors AB, BC, and CD. Therefore, the EMF induced in the concentrated windings can be represented by AB plus BC plus CD, and equal to 3AB, where AB equal BC equal CD. Therefore, KD can be represented by the phasor AD over 3AB. Now, to make this formula more general, the formula of KD can be represented by AD over MAB. Now, from this relationship of KD, we need to identify AD and AB in terms of M and beta. Let's start to identify the phasor AD. The phasor AD can be calculated by focusing on half of the triangle OAD, which is OAN. Note that AN is equal to ND, therefore the phasor AD can be represented by 2 times AN. By focusing on the triangle OAN, AN can be calculated and equal to OA sine M beta over 2. Therefore, the phasor AD will equal to 2 OA sine M beta over 2. Now let's identify the phasor AB. The phasor AB can be calculated by focusing on half of the triangle OAB, which is the triangle OAM. Note that AM is equal to MB. Therefore, the phasor AB can be represented by 2 times AM. By focusing on the triangle OAM, AM can be calculated and equal to OA sine beta over 2. Therefore, the phasor AB will equal to 2 OA sine beta over 2. Now, since we already identified the magnitude of phasor AD and the phasor AB, the distribution factor KD can be identified and equal to KD equal sine M beta over 2 over M sine beta over 2. Note that the value of the distribution factor KD is always less than 1 in case of the distributed windings machine. Now pay attention to this important point. The armature back EMF induced voltage ER generated from the rotor rotating magnetic field usually consist of the first component, or the fundamental component, plus harmonic components. However, we initially ignored the harmonic components to simplify the analysis. Now, if we ignore the harmonic components and use distributed coils or windings, the distributed factor Kd that we derived will represent the distribution factor of the fundamental components. It is very important to know that the harmonics of the induced EMF voltage in the practical machines can be significant and cannot be ignored. Therefore, we need to consider the fundamental component plus the harmonic components, which includes the third component, fifth components, seventh components, ninth components, 11th components, and so on. That means if we use distributed windings or coils, each of these harmonic components, including the fundamental component, will have its own distribution factor. In other words, the fundamental component has distribution factor Kd1, the third order harmonic component has distribution factor Kd3, the fifth order harmonic has distribution factor Kd5, and so on. The important point we would like to emphasize here is that all these components will be having some reduction in voltage by certain distribution factor when we use distributed windings. Now, to consider the distribution factors for the harmonics, the distribution factor Kd, which we derived earlier, need to be written in more general form to cover the fundamental component and any harmonic components as follows. As we can see, we added the variable n to the distribution factor, where n represents the harmonic component order. For example, if n equal to 1, then the distribution factor will represent the distribution factor of the fundamental component of the back EMF voltage ER. If n equal to 3, then the distribution factor will represent the distribution factor of the third order harmonic of back EMF induced voltage ER. Basically, every component of the back EMF induced voltage will have its own distribution factor. Now let's take an example. Assume we have synchronous machine with distributed windings that have slot angle beta equal to 12 degree electrical and slots per pole per phase M equal to 3. The distribution factor of the induced voltage components up to 11 harmonics can be calculated as follows. From the result of this example, we can conclude a couple of important points. The first point is that the distribution factors or the reduction factors of the fundamental and all harmonic components are less than 1. Also, we can notice that the fundamental component has largest distribution factor comparing with the distribution factors of the harmonic components. If we focus on the fundamental component, the distribution factor of the fundamental component Kd1 is equal to 0.98. That means the percentage of phase voltage magnitude of the fundamental component is high and is equal to 98% of the concentrated windings voltage. That means the fundamental phase voltage of the distributed windings reduced by 2% only. Basically, during the design, the distribution factor of the fundamental component KD1 must be high to achieve high induced phase voltage as possible, while the distribution factors of the unwanted harmonic components must be low to achieve low voltage magnitude for the harmonics. The other important point is that the high-order harmonics, represented by the ninth and above, have low or negative value of distribution factors. That means the high-order harmonic components will be eliminated or reduced effectively. Note that using good rotor design also can reduce the high-order harmonic components of the induced back EMF voltage, as we discussed in previous lectures. At this point, we should know that a proper rotor design and a proper armature distributed windings design are both contributing in eliminating or reducing the high-order harmonics. The last important point is that using the distributed armature windings can also reduce the low-order harmonics. However, as we can see, the distribution factors of the low-order harmonic components still have high value. That means the low-order harmonics is still dominant and large when we use full-pitched distributed windings. That means we need to use more effective distributed windings design to reduce the low-order harmonics. Basically, we need to use short-pitched distributed windings instead of full-pitched distributed windings. We will explain this point in details in the coming lecture. From this lecture, we can conclude the following points. Distributed windings are used in practical machines because it improves the utilization of the armature. Full-pitched distributed windings cause reduction in the fundamental component by certain distribution factor Kd. This considered disadvantage because the machine is losing some of the main or fundamental voltage magnitude. Full-pitched distributed windings eliminate or reduce dramatically the high-order harmonic components. This considered advantage over the concentrated windings. Full-pitched distributed windings also reduce the low-order harmonic components. This considered advantage. However, the reduction of the low-order harmonic components is not effective enough. Therefore, short-pitched distributed windings are used to effectively reduce or eliminate the low-order harmonic components. This point will be discussed in the coming lecture. Let's conclude this lecture at this point, and we will continue in the next lecture. Let me know if you have any question. Also, make sure to subscribe to this channel so you don't miss any lecture. Thanks for listening. I'm Ihsan Al-Nabi, and it was a pleasure sharing this lecture with you. Thank you.